All right, everybody, welcome to the video here for lesson number 10 on modeling with exponential functions. So like the last video, this whole video is going to be on the entire lesson. If you don't feel like you need the video for the lesson, you just want to check out the homework answers or see how to do the homework questions, just fast forward to there. All right, but let's start here with the opening exercise. So one of the things that we have to be able to do for these exponential modeling questions is be able to convert percentages to rates. So being able to convert these to decimals. So for 4%, we have 0.04. For 3.2%, move that decimal place 2 times, 0.032. 16%, we have 0.167. 50%, we have 0.5. And 3.14%, 0.0314. Don't lose any of those decimals. So what we're doing in today's is, or in lesson number 10 here, is we're extending what we've done over the last couple lessons and just looking at different models that we can kind of go with. So these are going to not be as much about money as the last couple lessons. So the first problem here talks about Red Hook. It has a population of 6,200 people, and it's growing at a rate of 8% per year. It then asks us to write a function that models this population. So since it's per year, it doesn't say the word continuously. It's not compounding in different ways, right? You can just use the regular equation, the future equation of P times 1 plus R to the T. So we just want to use the correct variables. So we have P of T is equal to 6,200 times 1 plus the rate, 8%, all to the T. Clean it up a little bit inside. So I have 6,200, 1 plus 0.08, all to the T. And it says, what is the predicted population for Red Hook in 2017? All right, so since this is since 2014, I have to figure out how many years between 2014 and 2017. All right, so that would be 3 years. So I could say the T value is 3. So I'll evaluate P of 3. So I have 6,200 times 1.08 to the third power. And if you do that, we want to estimate that population. We're going to get a decimal, right? We're going to get a decimal. We're going to round that decimal. So we're estimated at 7810. Number 2 says the function v of t represents the value in dollars of a comic book after it's purchased. So the value here is going up, right? So it wants us to state the initial value of the comic book and its yearly rate of appreciation. Appreciation is the fancy way of saying getting more money, right, or becoming more valuable. So the initial value is going to be $13.50. And 1 plus 0.017 is going to be the rate. So if we subtract the 1, the rate here winds up being 0.017. So we can see the yearly rate of appreciation is 1.7%. Now we can also do some decay questions here. So again, it doesn't always have to be about money. So here we have a question about Doug drinking a cup of tea. So it has 130 milligrams of caffeine. That's the initial amount of caffeine, right? And in every hour, the caffeine diminishes by 12%. So we want to write a function of C in terms of hours. One of the things to always look for is make sure that the time constraints are the same. So hours to hours, meaning your variable is going to be hours. So we can say C of T is equal to 130 times 1 minus, to make it decay, 0.12, all to the T, where T represents the number of hours of caffeine being in your body. Clean it up a little bit, and we get 0.88 in that parenthesis. Number 4, all right, here we have to kind of really take into consideration our time. And this is kind of a tough question, right? So it says in 1900, the United States population was 76.2 million people. And every decade or every 10 years, the population increases by 13.6%. Write a function of P of T, the population in years. So what we have here is we have a matching percentage to a matching number of years, but we want to represent our exponent as the actual true number of years that we have. So we're going to say P of t is equal to the initial amount of people, 76.2 million. I don't have to write it all out as million people, just know that your answer is in terms of million people. And then we can say is 1.136, right? So I'm taking 1 plus 0.136. That's where that parenthesis came from. Nothing there is different. What is different is our exponent. So our exponent has to represent the number of times, or we have the number of years that we have divided by 10. Why divided by 10? Because it says every 10 years we're getting that percentage. So if I have this for 20 years, my exponent has to represent 2, because I'm going to have 2 compounds of this interest rate. So I'm going to say the number of years, t, divided by 10. We'll use this also eventually throughout this lesson when we start to look at half-lives. So there's your function. And remember, the function's in terms of millions. So if I plug in something there and I get an answer of 82.5, it's 82.5 million people. Then it says, use your model to predict the number of people in the United States for this year. So we have to figure out how many years it's been since 1900. All right, so we're in the year 2019. So I can say T is 119 years. So I want to figure out what is P of 119. Next year, this will work out really nicely because it'll be a decade. But hey, all good. So we have 76.2 million people times 1.136, all to the 119 divided by 10. And then I'm just plugging it right into our calculator, right? So I could say P of 119 is equal to whatever that comes out to be. Just give me a second to type it in. 76.2, 1.136 to the exponent of 119 divided by 10. So we have 347.5 million people. Right? Then it says, what is the yearly percent rate of growth based on your model? Right? So this 13.6% only really represents the decade growth. I want to represent the yearly growth. So to make that yearly growth, I want to make the exponent just t to represent years. So instead of this whole thing, I really just care about what's here, right? So I just care about what's right here. So I'm going to rewrite that as 1.136 all to the 1/10th power, all to the number of years t. Now that 76.2, that's going to stay. That initial amount's not going to change. So if I rewrite this in terms of the yearly rate, so if I type into my calculator 1.136 to the 1/10th power, I get 1.01283. all to the t, where t represents years now. Again, I'm just rounding out. I'm just going 4 significant digits. So if I subtract this, remember, is 1 plus r. So if I subtract 1 from this, I can see that the yearly rate is 0.01283, or 1.283%. Keep going. So one of the things that we have to be able to do as well, and something that definitely will come up on the Regents exam, or at least your test for this chapter, is going to be a half-life. So half-lives is something that you learn about in chemistry. I think you actually even learn about them in earth science a little bit. So essentially, every element has an amount of time that it takes for half of its matter to decay away. So these things are called half-lives, right? There are going to be some things that sound challenging but really aren't. So when you're reading through the problem, it's going to talk about some kind of compound. It might say it's organic matter, or it might say it's a radioactive biisotopic something. It doesn't matter, right? It's going to be a bunch of chemistry words in there. All we really care about is how long it takes to have a half-life, and we have to figure out how much the sample started with. All right, so it says carbon-14, so that's just the name of carbon. The number 14 is meaningless, is used for dating organic matter. It says its half-life is 5,730 years. Consider if you have a 100-gram sample of carbon-14, how many grams is left after 5,730 years? So if it's half the life, right, so we could say 1 half-life is going to be 50 grams of this carbon-14. How many half-lives is 17,190? So that'll be 3 half-lives. So what we're saying is we're starting with 100, dividing it by 2 and getting 50. That's 1 half-life. We're then taking 50 and dividing it by 2. That's 2 half-lives. We're then taking 25 and dividing it by 2 for the third half-life of 12.5 grams. Notice we're repeating the same thing every single time. What are we doing every single time, right? We're dividing by 2, right? Would the same thing happen if we started with 1,000 grams? So after 1 half-life, we'd be at 500 grams. Then after the second half-life, we'd be at 250 grams. And then after the third half-life, we'd be at 125 grams. So each time we take a half-life, we're dividing by 2. So if I want to write a function that's repeating the value of divide by 2, instead of using division, I could use multiplication. So how could I repeatedly divide by 2? I can repeatedly multiply by 1/2. And remember, whenever I do something repeatedly in a math class, we can use exponents to show that. So to write a function here, I'm going to say a of t is equal to 500 grams of carbon-14. That's the initial amount, just like all the other functions we've done. The thing is, what's being repeated is not the annual percentage rate or the percentage rate over the course of months or the continuous value of E. It's 1/2. I'm repeating the value 1/2 over and over and over again. Now, how many times am I repeating this value? So if I look for half-lives, it's just the number of times I'm using 5,730 years. So every 5,730 years, I'm having another half-life or another multiplication of a half. So if I take the total amount of years that I have and divide it by 5,730, that exponent will determine how many half-lives I have. So there's my function for 50 grams. Essentially, to simplify it a little bit, because this is something, it's not really a formula that you have to memorize like the other ones, it's just something you have to be able to create yourself. This number in front is always the initial value. This number is always half for half-life. And this exponent is always t divided by the half-life. How long does it take to make the half-life happen? So then we can figure out, well, what percentage of carbon-14 is left after 3,000 years, right? So we could say, all right, so I have this initial value of 500. I don't know this ending value, but I do know that it's going to take 3,000 years. So I have 500 at 1/2 times 3,000 divided by 5,730. So it's a part of a half-life. It's not a full half-life, but we're still going to decay a little bit. So if I do that, I wind up getting the value of A of 3,000 is equal to 347. Now it says what percentage is left. So if I take 347 and divide it by the original sample of 500, right? So if we do 347 divided by 500, we get 0.694, or about 69.4% left. Then it says, use properties of exponents to change your model to highlight the yearly rate of decay. So again, we have a half-life here. I want to get it so that the value in the exponent's just t to represent years. So I have a of t is equal to 500 times 1/2 to the exponent of 1 over 5,730 all to the t. Just like I did in previous lessons, I want to isolate the exponent of t, so it's years now. So then if I plug that into my calculator, so I'm going to use 0.5, it's just easier to type in, right? You could use 1/2, it doesn't matter. And we get this, we see that a of t is equal to that initial sample of 500, so that's not going to change. And we have 0.9997879 ... all to the t power, right? Now, normally we would just round out 4 decimal places, so I could even get rid of this part and just say that's going to round to 0.9999 to the t, or the yearly rate of decay is what? Well, since it's a rate of decay, right, this is going to be 1 minus r in here. So if I have 1 minus r equals 0.9999, and I subtract 1, I get negative r equals negative 0.0001, or the rate is equal to 0.0001, or we could even say it's 0.01% per year, which is really, really small percentage, but it's because it takes a really, really long time to have half the sample. 5,000 something years is a really long time, okay? So let's see one here that's a little bit less of a time so we could do a little bit more stuff with it. So titanium-44, another sample here. This one says a radioactive isotope. That means nothing to you. That's just chemistry stuff. So it says every 63 years it decreases by half. As soon as you see decreases by half, or we're talking about a sample getting half as big or something like that, this is talking about half-life. Why is this not working? Oh, there we go. Okay, so we're decreasing something here by half. So it says for a sample of this, there's 100 grams left, write a function that defines this amount. So I could say titanium of T, we have 100 grams. It's a half-life, so 1/2 is the base of the exponent, and it's the amount of time over 63 years. So we know T is years. We know T of T is the amount left after T years. Those are only 2 variables. That's pretty simple. Then it says how much is left after 40 years. So I could say T of 40 is equal to 100 times 1/2 to the 40 over 63. Type that into our calculator, and we get 64.4 grams. I think it's grams. Let's see. Yeah, grams. Then it says use properties of exponents to write a new function that reveals the yearly percent of decay. So to write a new function here, we still have 100, we still have 1/2, but we have T over 63. Now I want to isolate it so that T is the only exponent, so that years is my exponent. So I'll raise 1/2 to the 1 over 63 exponent. If I do 0.5 to the 1 over 63, I get a value there of 100 times 0.9891 to the T. So again, what's in that parenthesis doesn't represent 1 plus r, it represents 1 minus r. That's what this is. These are equal to each other. So I could say 1 minus r equals 0.9891, subtract 1 from both sides. Negative r is equal to negative whatever the heck that is, 0.0109. So I can say the rate is 0.0109, or the rate as a percent is 1.09%. That's my yearly rate. Right? On to the homework. So if you're just joining us because you're a homework only person, that's totally cool. Right? So let's see how we're doing here on the homework assignment. So it says write an equation that will model the population of initial size of 625 that is growing at an annual rate of 8.5%, right? So we have a function, we'll say population after time is equal to initial size of 625. Now we have 1 plus 0.085 for the number of years. So that would be T. So we can simplify that by cleaning it up a little bit. There we go. Number 2 says, as water drains out of a pool, the depth of the water decreases at a constant percent rate of 20% per hour. So this is going to be a decay function. It says the depth of the water when draining begins at 12 feet. That's the initial value. Find the depth of the water to the nearest tenth after 7 hours. So let's first write our function. So we say the depth of the water after a certain number of hours is equal to the original depth times 1 minus 0.2, all to the number of hours. So notice, instead of years, I'm just using this as terms of hours. We don't have to do any conversions here, all right? So I could say d of h is equal to 12 times 0.8 to the h power. Now, if I find d of 7, I'll know how much water is left after 7 hours. So I could say 12 times 0.8 to the 7th power. So 12 times 0.8 to the 7th power is approximately 2.5. So we have 2.5 feet left of water. Number 3 says there are 400 bacteria in a petri dish. The bacteria triple every 4 hours. This is almost like Half-Life, but instead of halving every so often, it's tripling every so often. So it's the same idea. So I'm going to say B of T is equal to the original amount of 400, but every 4 hours, we're tripling in size. So every 4 hours, I want to multiply the previous value by 3. So I'm going to say a base of 3. And the exponent is going to be the total number of hours divided by 4 to represent each time we multiply by 3. How many bacteria are after 10 hours? So I could say, what is B of 10? So that's 400 times 3 to the 10 over 4. Plug that into my trusty calculator that we all totally bring to class every single day. Right, Zach? So we say B of 10 is equal to 6,235 bacteria. You can even say 0.4. Number 4 says hydrogen-3 has a half-life of 12.31 years. Consider a 50-gram sample of hydrogen-3 and write a function after h or t years. So if h of t is equal to our 50-gram initial value, it's a half-life, so every so often we're going to multiply the previous value by half. And to figure out how long it takes for that to happen, we do t divided by the half-life. How much of this sample is left after 30 years? So I'm just going to find out, well, what is h of 30? So we'd say 50 times 1/2 to the 30 divided by 12.31. Should be getting smaller, so it's about 9.23. Doesn't say what to round to on a test, I'd be specific. And then it says determine and state the yearly percent rate of hydrogen-3. So to find the yearly percent rate, I really just care about the 1/2, and I want to raise it to the exponent of 1 over 12.31. So if I do 0.5 to the exponent of 1 divided by 12.31, I get 0.9452. And that is not the rate. That is 1 minus the rate, right? So we could say the rate is going to be 1 minus that number. So the rate is going to be 0.0548, and then change it to a percentage, so we have 5.5%, something around there. That's it, right? Hopefully this video helped. Hopefully you're making out well as we move forward here in this chapter, right? Just know that everything is kind of related. So if you missed a lesson previously, just go back to that lesson and you should be okay. Okay, best of luck with your homework, and I will see you all tomorrow.